Hello everyone again, and thanks. I would like to thank to the organizers for this opportunity to present some results on this project. My name is Abel, and I am a PhD student at the Institute of Astronomy from the National Autonomous University of Mexico, or UNAM in Spanish. So I am going to talk about a study that we have been performing on the M-type Mira star RCAR in the K-band. So let me give you a brief context or scientific motivation. First starts with masses up to 8 solar masses evolved to the asymmetric giant branch phase, and then they transform into planetary nebulae. During this AGB phase, the stars experience mass loss events, and all their processed material is returned to the interstellar medium, contributing to its enrichment. However, the mass loss processes are better constrained for carbon-rich stars with a carbon-to-oxygen ratio larger than 1 than for oxygen-rich stars with carbon-to-oxygen ratio less than 1. So I will explain you why in the next slide. One way to understand or constrain these mass loss processes in oxygen-rich AGB stars is through images of their most inner parts. And here, interferometry allows us to achieve the highest angular resolution to map these inner structures. These are some examples where interferometry plays an important role in characterizing the different structures on above the stars. Now, how is the radiation interacting with matter in the closer vicinity of these AGB stars? Well, this is a very simplified sketch of what we think is happening. The radiation pressure acts efficiently on the molecules formed around carbon-rich stars through absorption. So this interaction is the one that mostly drives the winds on these stars. However, the molecules formed around M-type or oxygen-rich AGB stars are mostly transparent to the near-infrared radiation. So the interaction is not as efficient to drive the winds. Therefore, another mechanism is needed to explain these observed winds and envelopes. Hofner et al. In 2008 proposed that under certain conditions, the dust grains can grow to sizes in the order of microns. So the radiation interacts more efficiently on these grains through scattering. However, in this case, in K-band, we can't see the dust as it is transparent. But we can see the gas. In particular, CO is a very stable molecule against dissociation, and in principle, allows us to trace the dust distribution over a wide radial range. Moreover, whether the dust gas distribution is clumpy or not, it is important as it also affects the dust production and growth. According to Hofner and Olofsson in 2018, a clumpy medium will affect the chemistry, including the ability of the molecules to survive dissociating radiation. So we want to trace the CO around an oxygen-rich star. And to perform our studies, we selected this star, RCAR, because it is a prototypical M-type or oxygen-rich star that is very bright in the near infrared, as you can see here. But it also is close to us, so we can resolve its inner structure. On the left, I show you a reconstructed image from 2014 in the H-band. In this case, you can see its internal structure, but the presence of a circumstellar environment was not confirmed. So RCAR, for our studies, RCAR was observed during January and February of 2018 using the instrument gravity at the VLTI, using the small auxiliary telescopes configuration, and with a spectral resolution of 4000. On the right, I show you the configuration and the corresponding baseline lengths. An example of the calibrated squared visibilities and closure phases can be found in this slide. To perform our analysis, we selected 3 spectral intervals, the ones that I show you here. We called the pseudo-continuum to the entire region between 2 and 2 microns. The first bandhead here, and the second bandhead here. And on this side, you can see the spectral ranges and the corresponding spectral channels that we selected and analyzed. From now on, when I talk about these labels, I will refer you will know which interval I'm talking about. These are the normalized spectra. The drops at 2.29 and 2.22 microns correspond to the location of the first and second CO vibro-rotational transitions, respectively. So the first step in our analysis was to characterize the size of the star at the 3 different spectral channels. intervals, sorry. So we fit a Gaussian function to the squared visibilities as a function of the spatial frequency. Here you can see the functional form where U and B correspond to the spatial frequencies, and theta is the full width at half maximum of this Gaussian. And we can interpret this value as the apparent size of the source. These plots here show the full width of the full width at half maximum versus the wavelength for all three intervals. The trend observed in this plot is due to the presence of water and CO plus water that are located in more extended regions than the pseudo-continuum emitting region, which we think is located at 2.25 microns approximately. We can also see a different size estimation due to the variability of the star. So the maximum difference at 2.25 microns is around 2 milliarc seconds. These two plots correspond to the first and second CO transitions. We do not see the changes here between epochs, as the CO is less affected by the changes in the surface of the star. And from now on, due to the time, I will only show the results corresponding to the first CO bandhead. So next, we wanted to estimate some astrophysical parameters corresponding to the CO. Therefore, we used a model with more physical meaning. In this case, the model we used is known as the single layer model. This model consists of a central source that emits as a black body, and it is surrounded by a layer with no geometrical thickness. This layer absorbs the radiation coming from the star and re-emits again as a black body. The parameters that we estimate using this model are the temperature, the radius, or the size and optical thickness of the layer. And to estimate the mentioned parameters, we began by estimating the optical thickness through a direct fit of the spectrum. Then we use this value to estimate the temperature and size through a fit to the squared visibilities. In this table, I show you the mean values that we found. With these values, we estimated a column density that it's around 10 to the 19 centimeters at -2. All the values here are more or less in agreement with the estimations found by other authors that also use a single layer model to estimate the parameters for other oxygen-rich AGB stars. We found that the medium is optically thick, and also, as you see, we are calculating a relatively high column density. So we suspect that this combination is enough to shield the dust grains, allowing them to grow until they reach micron sizes. As I mentioned before, the interaction with the radiation becomes efficient through scattering. But we are still working on this hypothesis, so we need to perform more studies. Until now, the models that I showed you do not take into account the asymmetries present in the structure of the source. So to have a more quantitative estimate of its morphology, we performed the image reconstruction using the squared visibilities and closure phases. And we performed this image reconstruction on the 3 spectral intervals that I showed you before. These are the images corresponding to the January epoch, and these are the images corresponding to the January epoch at the first CO bandhead. By visual inspection, maybe or maybe not, you can see there are differences between epochs, because the structures observed in one epoch are different from the ones observed in the other epoch. But also, we can see differences between spectral channels at the same epoch. However, and to have a more precise characterization of these asymmetries in our images, we used a principal component analysis. The principal component analysis has proven to be very useful when extracting and characterizing the information contained in a set of images. Medeiros et al. In 2018 demonstrated that the visibilities of the principal components are equal to the principal components of the visibilities. So this method is useful for us to trace which changes across a set of images affect more the visibility profile, which includes the visibilities and the square visibilities and the closure phases. So we calculated the principal components for each spectral interval. The principal results from this analysis is that we found that around 90% of the variance is stored in the first 4 principal components that I show you in this slide. These first principal components indicate asymmetries located at different positions. And as we also see, the principal components are different between epochs. So we suspect that these asymmetries observed might be related to a clumpy CO distribution, although we cannot characterize this distribution as we do not have enough spatial resolution. And finally, as my conclusions, we established the size of our car in the K-band through a geometrical model fitting applied to the squared visibilities. We found that there is a wavelength dependence in the estimated size due to the presence of molecules like water and CO, but also we found a maximum difference of 2 milliarc seconds between the two epochs due to the variable nature of the source. By using a single layer model, we established some important astrophysical parameters at first order. In particular, we found that the CO is optically thick, and combined with the average column density that we found, we suspect that the gas can act as a shield to protect the dust from the radiation, allowing it to grow and to reach sizes in the order of microns. And at these sizes, the radiation acts efficiently through scattering, driving the winds observed on this type of stars. However, we are still working on this hypothesis. And through an image reconstruction and principal component analysis, we found that the observed principal components show that CO has a clumpy distribution. However, we cannot characterize these clumps as we do not have enough angular resolution to map these finer structures. But we, in the future, we aim at characterizing these structures by obtaining higher angular data. So by my part, it's all. Thank you very much for your attention.
Hey, thank you very much for the talk. And we'll look for questions in the audience and online. We have a question online. Oh. Jin Hao, is that?
Okay, thank you. And Abel, thank you very much for the very nice talk. And I just want to know what's the noise in your maps, reconstructed maps. You are talking about clumpiness, but we should always warn about the possible uncertainties. Maybe you are analyzing the uncertainties in the maps, the clumpiness.
In these maps?
Yeah.
Well, for the maps, I don't have now actually the noise, but in the structures in the reconstructed images, the structures that we can believe are about 10% of the intensity, which is the more
okay. Yeah. Okay.
The other yes, contour, but here I'm still in the process of calculating.
Mm-hmm.
Yes.
Okay. Thank you.
Thank you.
Okay, and we could go with Conrad next.
Yes, my question is very related. Actually, I'm wondering how much your principal component analysis is influenced by subtle differences in the UV coverage you have for the different epochs. So I'm really wondering if, like, the analysis would probably in the end be better done in the UV space rather than in the real image space.
Yes, we are planning also to perform the principal component analysis in the square visibilities, but for now we began with the analysis in the images, but we want to also perform the analysis on the visibilities and then compare and see what the differences are. Yes.
Okay, and we have a question in the chat window from Kishi Onaka, who asks, what was the variability phase?
The variability phase between one epoch and the other is around 0.11, as I remember, if I remember well.
Okay, any other questions? All right, let's thank our speaker again.